The third way of constructing control chart using the proportion data is the MP chart. So what does MP stands for? MP is the number of defects per sample group. Okay, so we all know that P bar represents for the average fraction rate or proportion of defect. If you multiply n, which is the sample size, that will give you expected number of defects in each sample group. Right? If the defect rate is 15%, we see 15 out of 100 each time. So we based on this to construct a center line. Right? If you look at the formula for center line, you're adding all the defects from each group and you divide it by the number of groups. Right? In total, let's say if you're using k equal 20 and total defects was, if your total defects was 10, you have 10 groups, and each group, on average, you had half count of defects. Okay? Or maybe I give you another example. Let's say in this case, you're using k of 10, but in total, you had 115 defects on your 10 groups of sample. That means you're expecting, in average, 11.5 defects in each sample group. So that will be your center line. And this is a standard error. Okay, this is standard error. You still use the 3 control limits, 3 standard deviation control limit to construct upper and lower control limits. Okay, see the relations between N and P and MP. So this is pretty obvious, right? When you have MP bar, if you know your sample size, okay, you can calculate the P bar easily, which in this case is this, right? So as long as 2 things are provided, 1 thing can be calculated automatically. So again, this is what it is. You're seeing the total K here is 25. I will show you from Excel later. You have to add them up. Oops, sorry. You have to add them up, and you divide it. You divide the sum with a 25. That will give you the MP bar, which is your center line. Judging from here, it looks like 2.2, right? That must give you what's the total number of defects in this 25 group observations. And then once you have MP bar, you can construct the upper and lower control limit, and that will do the job. Okay, so these are everything for the fraction-based non-conformance, right? These are the control chart for the fractions. If you review what we have done, we discussed the constant sample size case. We discussed a variable sample size case, right? When it is constant, you can directly use P bar or MP chart easily. But when the sample size is different from group to group, you either choose to use the N bar or NI. So in this case, you'll be having variable control limits from group to group. In this case, you'll be seeing a constant control limit from group to group, but you can use it without assessing whether it is applicable or not before you use it. Okay, all the sample size needs to be falling between certain range. Okay, certain range such that 25% smaller or 25% larger. The auto sample size has to be located between this 2 range for you to be able to use this approach. Okay, for a variable control limit, it was pretty straightforward. So for that, let's move on to the number of conformance based approach. So you may be wondering, what is the difference between this NP chart and the number of conformance-based approach. So when we come out with an NP chart, this is basically the fraction-based approach. Even though we're talking about the count here, our primary measure was still fraction, okay? But here, from this particular type of data, we are directly looking at the count of nonconformances without considering the fractions, okay? Because fraction follows normal distribution, but the count actually follows the Poisson distribution, as I stated earlier. So let's begin with the C-chart. So basically, C-chart is used when the number of opportunities for non-conformances in each sampling unit is constant. What does that even mean? So if you look at these examples, it will become very clear. So for example, number of distressed packages per full 40 feet containers load, okay, or number of discoloration per 3 square feet fabric, or number of soldier death from horse kick wounds per army corpse. So this is actually actual example that scholars used to introduce the Poisson distribution. So if you examine all these examples closely, they all have the same size of opportunities of making mistakes. The size of opportunities in the sampling unit are the same, right? I don't know if that sentence makes sense to you. This is the best I can come out with. The size of the opportunities in the sampling unit are the same. So there are so many packages you can feed in to a full 40 feet container load. And there are so many mistakes you can make in per 3 square feet fabrics, right? The per army corpse, the size of the per army corpse is going to be the constant, right? It's typically ranging between 20,000 to 45,000, at least according to Wikipedia, that is so. So assuming that the army corps that you're studying over the year sticking to the same size of 20,000, in that case, the maximum soldier death from the horse kick wound is going to be 20,000. Therefore, that's what I'm saying here. The size of opportunities in the sampling unit are the same. Okay, so a center line is basically very simple. So the average in this case is basically the average of the defects, right? C here is the count of nonconformances or defect. K is number of sample groups. And like I said, variance of the Poisson is the same with the average itself. Therefore, you are seeing standard deviation is equal to square root of the average. Okay, with that you can easily construct lower control limit, upper control limit. This is what you're seeing from here. Table shows the number of machine failure over a 25-day period, right? Number of machine failure over a 25-day period. Please use an appropriate techniques to construct a control chart. So think, I'm adopting this example from textbook, therefore I know there's some conditions I should have put it in there. So this actually indicates that you have the same constant finite number of machines that make mistakes in each day. Okay, in other words, it implies the same size of opportunities from each sample. So therefore, it's easily you can use the C-bar chart. Okay, so what is the center line? It is the sum of column 2 divided by 25, because you have total 25 samples. That gives you the average number of samples. You use that and you can calculate the standard deviation, the square root of C bar, and of course you can construct upper control and lower control limit by using 3 standard deviation control. Okay, I hope that makes sense to you. And the last one is the U chart. It's the variation of U chart, but it has slight difference. The difference coming from the number of opportunities for non-conformances in each sampling unit is not constant. Okay, so for example, number of errors per patient. Okay, number of maybe medication error or injection error, because number of patients the visiting hospital each day is different. Therefore, the base number of patients in which you use to measure the errors are different from day to day. Okay, so also the cells made per call. Okay, cells made per call. So you may be making different numbers of phone calls each day. Okay, out of that number of phone calls, the certain phone calls will be landed as a cells, some are not. Therefore, the base number, which is number of phone calls you made, are different from case to case. Number of complaints per customers, right? Again, the number of customers will be different from time to time. Therefore, the base size of opportunity, the size of opportunities in the sampling unit, not the constant. So in that case, you'll be using this approach, right? For the center line, you'll be using this formula. Number of error for the first sample size, right? So if you look at the numerator, it's adding all the defects or non-conformances together. For the denominator, you're adding all the sample sizes together. That gives you the center line. And for the standard error, the standard error follows this. Okay, so it implies that each sample will have its own standard error. Therefore, it will be generating a variable control limit chart, just like we've seen one from the previous occasion. Okay, so each control limit is different. I should probably have indicated that each control limit is different. Each control limit for sample group I is different. Okay, again, if you see this, sample unit size is different from case to case. The number of conformance is of course different. Therefore, use the U bar is equal to total, or the sum, of column 2 divided by sum of column 3, right? And you see the control limit is quite messy. It's different from the sample to sample. That is because the base opportunity is different. The size of base opportunity is, the base of the, let me rephrase it. The size of the base opportunities in the sampling units are different. That is why you're seeing the different control limit from sample to sample. This gives you all the needed formulas for all the control charts we have learned so far. But really, there are two types, and measurements based on the measurements. There are really two types based on the measurements. Variable measurements use two charts, X bar and R bar, or X bar or S, or X bar or MR. Depends on the sample size, right? With the attribute data, depending on whether you're using fraction or count. In fraction, you use P bar or NP bar. In the count, you use C bar and U bar. Depends on the base size of the opportunities. Okay, so I'll stop here. I'll be demonstrating all the Excels in a separate video.